Continuing our mechanical energy conservation example scenario, following our cart now launching off the end of the ramp here at moment 2 with a speed v2 we know, launching at a 60-degree angle with a height that we know as well, y2 above our vertical reference point down here. From that point, it becomes a projectile, and at the apex of its parabolic path, we're calling that moment 3. The cart will have a velocity v3. We would like to find its speed at moment 3 and this height y3. And the question will be, do we even need to use energy principles to do this, or can we fall back on physics that we already know? So I'll ask you to pause the video in a moment and consider, could you just use dynamics and kinematics to solve for the speed here at moment 3, given y2 and v2 and that angle? Is that enough information to use these techniques, or will we need to appeal to energy principles to answer this question? Pause the video and consider your answer. Ready? Your answer should be yes, we can use the physics we already know about projectile motion, because we know that the x component of the velocity of a projectile is constant while it's in free fall. So this little vx here at moment 2, that will be identical to our speed here at moment 3. The speed at 3 is purely horizontal, since that's the high point of our path, and our velocity is always tangent to the path, so it's purely horizontal at the high point. So it's identical to the x component at moment 3, which is identical to the x component at moment 2, which we can find from trig back here, knowing speed 2 cosine 60 degrees. So that 3.8 meters per second, that's this vx here, that's our speed at moment 3 as well. So we've answered that. There's no need to consider energy to address that question. Next question, the height y3 at the highest point on the projectile's path. Think here and pause the video in a moment to do so. Could you use dynamics and kinematics to solve for the height at moment 3, given what we already know? Are these sufficient, or will we need to use energy principles to find that? Pause the video and come up with your answer, why or why not. Ready? Your answer should be, again, yes, we can, of course, use Newton's second law and constant acceleration equations, because our projectile being in free fall could we could apply this constant acceleration equation to our object, given that it's the y component of its velocity at moment 3 is going to be 0. We know the y component of its velocity at moment 2. We know its acceleration in the y direction while it's in free fall, and our delta y is y final minus y initial, y3 minus y2. So we could use this kinematics equation to solve for y3. No need for energy here. Nevertheless, here I want to show how we could use conservation of energy to find that height. And let's end up comparing the two methods. So let's start with the conservation of mechanical energy equation and consider the time interval from moment 2 launch to moment 3, the high point. And whenever using this equation, you have to ask yourself about the right-hand side over here. Are there any non-conservative forces present from moment 2 to moment 3? And we say no. The object is in free fall. The only force on it during that time is gravity, which is a conservative force. Therefore, the right-hand side of this equation is 0, which means that the change in mechanical energy of our system from moment 2 to 3 is 0, so energy at 2 can be set equal to the energy at moment 3. So we state this principle, and then we write this sequence of lines. Energy at 2 is the kinetic at 2 plus the gravitational potential at 2. And likewise at 3, the K3 plus the UG3. How do we know it has these two terms at those moments? Well, it's moving at 2, so it has kinetic energy, and it's above the reference point at 2, so it has gravitational potential. Likewise at 3, it's moving, so it has kinetic, and it's above, or more specifically, not at the reference point, so it has gravitational potential. So there's K and UG at both those points. expanding each energy into this sequence of terms here, and knowing that the final speed v3 we have just considered and worked out. So we know what that final speed is because it's identical to the x components of the velocity at moment 2. Looking through here, we see that there is a mass on every single term. So we could factor out a mass from both sides and then cancel it. So we've seen this feature before, that when the only energies are kinetic and gravitational potential, and when energy is conserved, the mass of your object has no effect on the motion. It's going to cancel out. We don't need to know the mass. And the thing we're trying to solve for is right here, y3. So at this point, we would just rearrange this algebraically to get y3 by itself and then plug in our values. So that will work. We can find y3 using this energy approach. But let's compare this equation here that we need to solve for y3. Let's compare that method to our earlier proposal using physics we already know, using projectile motion physics, using this constant acceleration kinematics equation. This we could rearrange and solve for y3. And comparing the two equations, the kinematics one is actually simpler. It's got fewer terms. It'll be easier to rearrange to get y3 by itself. So if either one of these equations works to solve for y3, we're going to prefer the simpler one. That'll be less effort for us. We're going to prefer the kinematics approach, even though the energy approach would work as well. The energy-based approach doesn't look easier in this case. Now, that doesn't mean that energy conservation is not a viable approach to projectiles. We just need to be smarter about it. So let me propose this. I still want to try to use energy conservation to find that height, y3, but I want our resulting equation to involve a little less algebra. So our strategy here is going to pick a different moment to pair with moment 3. So instead of considering the interval from moments 2 to 3, this part of the story here, let's consider the interval from 1 all the way to 3. Conservation of energy from moment 1 all the way to moment 3. We know that there is no work done by non-conservative forces at any time during that interval. Normal force doesn't do any work, gravity is not doing any work. So that means our mechanical energy of our system is conserved from moment 1 all the way to moment 3. There's actually no need to stop at moment 2. We can say that the energy at 1 equals the energy at 3 without involving moment 2 at all. And if we do that, we get a slightly easier problem to solve, or a slightly simpler algebra to deal with, because of this right here. At moment 1, the kinetic energy is 0 because the object started from rest. This term becomes 0, so at moment 1 it has only gravitational potential energy. The object has a simpler expression for its mechanical energy at moment 1 than it did back here at moment 2. At moment 2, it had both kinds of energy, so 2 terms. But at moment 1, only one kind of energy, only one term. That's a pretty significant simplification to the algebraic load we have ahead of us. Here's E3 on the right. That's the same as with our previous approach, the 2 to 3 approach. But now our 1 to 3 approach has just one term over here instead of 2, which makes our algebra considerably easier. We're going to then rearrange this to get y3 by itself in a few lines. Gets us to this expression here, plug in our given numerical values, including for v3 here, v2x, using the speed at v2 times cosine of 60 degrees to get that v2x, and we get our height at moment 3. There's the answer that we want. I want to compare this back to the kinematics approach. We wrote down this equation earlier, this constant acceleration equation for the y direction. We could rearrange this to solve for y3 and get a similar expression, plug our numbers in, and of course find the same answer. So we can solve for y3 either using kinematics or using energy. And I would say that these two approaches are require an equal amount of effort. They're comparable to each other, at least. The energy-based approach is not easier than kinematics. It's similar. That is, if we're strategic about it and pick convenient moments to work with. If we pick a convenient moment, then using energy is just as convenient as using kinematics. Uh, if we're not strategic about it and make a poor choice of moment, then energy can be more complex and not worth the trouble. So we want to continue to hone our instincts for making strategic choices in moments to compare in scenarios so that we get energy-based uh, equations that are as simple as possible to solve.